Okay guys, in the last lesson we talked about the sort of scope of space and time when operating RPO at GEO. Now in this lesson we're going to kind of talk about the maneuver rules of thumb or approximations that you can use to very quickly calculate in-track, radial, and cross-track burns to do the motion that you want to produce. Now all of the rules that I'm going to show you, or the approximations, build on similar ideas. The first one that I want to show you, though, is the semi-major axis rule of thumb or approximation of thumb. Basically, the third rule is that if you increase your orbital altitude by 78 kilometers or decrease it, you will produce a 1 degree per day drift. Now, when we say 1 degree, we're talking about those longitudinal degrees that I talked about in the previous lesson. So because we often describe objects at GEO according to their longitude of the ascending node in degrees over the Earth. What I'm going to show you in this lesson is how do I move 1 degree longitude of the ascending node, or 2 degrees, or 3 degrees, or 4 degrees per day. Now this rule scales linearly, and what I mean by that is if you increase 78 kilometers, you will drift at 1 degree per day. If you increase by 2 times 78 kilometers, or 156 kilometers, you'll drift at 2 degrees per day. So let's just really quickly look at that. I've got RPO satellite 1 over here. It's 2 degrees away, and I want to get to that GeoSat point in only 24 hours. So really easy. I'll have to do some burns, but let's just say that I could increase my semi-major axis by 156 kilometers. So that's going to be 42322. And what you'll see when I run this is now that previous location, which was a perch on the GEO belt, is no longer stationary, but is now drifting to the west. And that's because I increased my semi-major axis. So here we see it. We're still 2 degrees away at the start. And in 1 day, 24 hours, I'm just going to advance 1 day, we should be directly over GeoSat. And sure enough, there you go. Okay, if that was too fast, then let's just back that down. We'll be 78 kilometers up only. So it'll be 42244. And okay, there you go. So now we're still starting out at that 2 degrees away. But now it's going to take us 2 days to get there. So let's look at where we're at the 4th of August. Boom, directly overhead of GeoSat. If you increase your semi-major axis above the GEO altitude, you will create a westward drift. If you decrease your semi-major axis below the GEO belt, you will create an eastward drift. So if we move RPO satellite to -1 degree longitude of the ascending node, and now we're going to drop our semi-major axis by 78, which is 42088. You'll see that I'm going to start out 1 degree away, and I'm going to drift to GeoSat in 24 hours. So here I am 1 degree away, and now I'm going to induce that drift. And sure enough, 24 hours later, I am directly below GeoSat. It's important to note that this isn't just a feature of linear drift. Your semi-major axis is the only thing that's actually governing your east-west drift. So it doesn't matter what your eccentricity is. So if we have something wild like this 0.01 degree eccentricity, we're still going to drift at 1 degree per day. And maybe it doesn't look like it intuitively, but let's just see where we are in 24 hours. If we did our math right, we started out 1 degree longitudinally away from GeoSat, and we should be directly under GeoSat, despite the fact that we have this now large drifting NMC. And sure enough, it works. Okay, that's all well and good, but I'm sure you guys are finally ready to start doing some maneuvers, right? We're here to do RPO. So how do I actually move and produce these drifts other than just going into SDK and changing my semi-major axis? What we're going to do is we're going to establish rule of thumb number 4, which is that performing a 2.84 meters per second in-track burn changes your semi-major axis by plus or minus 78, depending on if you do a plus or minus in-track burn. Okay, that 78 should stand out to you because that is our rule of thumb for 1 degree per day drift. So I've got RPO satellite here, 1 degree away from GeoSat, and I'm going to perform a 2.84 meters per second positive in-track burn. So here I have that set up, 0 radial, 2.84 meters per second in-track, and 0 cross-track. Just going to do that burn, and before we go look at the screen, we're just going to go look at our old COEs. So previously we had a 42166, that's the altitude of GEO. Just click refresh. We're going to see that it's now 244, which is that same number that we calculated when we were adding 78 kilometers to our drift. So now if we look at what we produced, we are now inducing a 1 degree to the west drift. And this is a cumulative effect, and I'll kind of show you what I mean by that. But here we've got a drifting NMC. You'll see that in 24 hours we reach Geosat. Boom, there we are. Okay, but what if we wanted to reach Geosat in 12 hours? You might be thinking, well, let's just double that 2.84 meters per second, right? That's not necessarily incorrect, but I'll show you why that's not necessarily the most ideal either. Okay, that burn is going to be 5.68 meters per second. That's just double 2.84. So what's going to happen if we do this? 5.68. Boom. All right, so now what you can see is a 2 degree per day drift. And we can pretty much see that it's 2 degrees because this is 1 degree here and pretty much 1 degree in the other direction. So now if we go 24 hours, we've moved 2 degrees, sure enough. And we can go back to the COEs. We just increased our semi-major axis by another 78 kilometers. But at 12 hours, where were we? Sure enough, rule of thumb number 1 comes back, the orbital period. We were at our point of apogee because we started at perigee. When you perform a positive in-track burn, that positive in-track burn becomes your new point of perigee because you are raising your semi-major axis. So you can see, if I just play this through, we're always going to hit that same point of perigee, which was the GEO belt where we started. What we've done is we've raised our semi-major axis by, in this instance, 156 kilometers. Because the semi-major axis is the average between your point of perigee and your point of apogee, your altitudes of apogee and perigee. If your altitude of perigee hasn't changed because you did a positive in-track burn, but your semi-major axis has changed, then you have to now increase your altitude of apogee so that that average equals plus 78 or plus 156 or whatever. So you can see here in our classic orbital elements, our perigee is still at 42166, which is the geosynchronous altitude. Our semi-major axis has increased by 156. So in order for this to be the average of these two numbers, this number had to increase by double 156. So you've got 42479 minus 42166. If I divide that by what I know I increased my semi-major axis by, which was 156, you'll see that it's approximately double that number. Which makes sense because when you add these two numbers and then divide them by 2, that's how you get the average. Okay guys, so I have lots of videos you can watch to learn how to combine in-track and in-track burns and in-track and radial burns and do Holman transfers and do fast transfers, Gaussian transfers, Lambert transfers, whatever you want to call them. So check these out if you're interested in how to combine in-track burns. The main thing I want you to understand is that the 2.84 meters per second burn to change your semi-major axis by 78 kilometers doesn't have to happen all in a single burn. It can happen in multiple burns. It can happen in non-inertial burns over time. It's just the concept is 2.84 meters per second applied in-track into your orbital velocity will increase or decrease, depending on the direction, the semi-major axis by 78 kilometers. Cool. So for your next rule of thumb, I want to give you a way to calculate radial burns in the exact same way, approximate that we are doing for in-track burns. So before I jump into the radial burn rule of thumb, first I want to show you the impact of the in-track burn and why it's identical to the rule of thumb we're going to establish for the radial burn. Okay, so here I have the 2.84 meters per second in-track burn that produces that 1 degree per day drift. And it increased my semi-major axis by 78 kilometers. And I also have this satellite, which is 78 kilometers directly above RPO satellite. And what I'm going to do is draw the apparent motion from RPO satellite to this 78 kilometer point satellite. So here we go, we have our GeoSat VVLH, and now we have a 78 kilometer up VVLH. And what you'll see is that drifting NMC from the perspective of GeoSat looks like just a standard NMC from the RPO in-track satellite. So let's just watch it. Okay, now think about the shape of this NMC and the size of it. It's a 78 semi-minor and 156 semi-major axis. So the way I like to think about this and how we establish our next rule of thumb for radial burns is that in that instant moment that we performed our burn, we created this point of apparent motion, which was at the center of this reference frame, the 78 kilometer up reference frame. So we kind of took our point of apparent motion, pulled it out of the body of our satellite, and put it 78 kilometers directly positive radial to us. And now we are appearing to NMC around that point. This is kind of a term that I call the relativistic barycenter. That is not a scientific term or a documented term. It's just something that I like to call it to have a thing to call it. You can also call it the point of apparent motion or whatever you want to call it. But the important thing is our 2.84 meters per second burn raised our point of apparent motion, our relativistic barycenter, up 78 kilometers. Cool. Now let's talk about our radial rule of thumb. So the radial rule of thumb states that if you perform a 2.84 meters per second radial burn, you will create an NMC that is 78 kilometers semi-major, 36 kilometers semi-minor. Okay, so how the heck are we going to use that, and what are you even talking about? Well, before I jump into that, I just want to say there is a caveat with this rule of thumb. It is, of all the things I've shown you today, much more of an approximation because it depends on your eccentricity that you're starting with, the relative eccentricity to the point you're trying to go to, where you are in your current true anomaly or arc-perigee, or how far you are away from arc-perigee. There's a lot of caveats with this. But if we imagine this initial use case where RPO sat has the same relative eccentricity as some point on the GEO orbit, then this rule of thumb works really nice and it scales linearly just like all the others. Okay, so all the legalese done. Let's just look at this rule. I've got a maneuver that is 2.84 meters per second positive radial, and it produces this NMC. And based on the rule of thumb, this NMC is going to be 156 kilometers across and 78 kilometers from apogee to perigee. Now, what's really fascinating about this is we have now created an NMC around a point that is 78 kilometers away from us. There you can watch it go. Boom. Does that not seem very similar to when we did the in-track burn and created an NMC around a point that was 78 kilometers up from it? It's incredibly similar, even though the shape of these NMCs is different. One is kind of targeting the major axis and one was targeting the minor axis. But the important point is our relativistic barycenter, or our point of apparent motion, or whatever you want to call it, has shifted by 78 kilometers. In this case, it shifted up away from the Earth, and that caused us to drift and create this larger NMC. But here, the radial burn can't change the semi-major axis, so it has now pushed our point of apparent motion 78 kilometers west of us. But very similar, we have taken sort of our relative motion out of the satellite and moved it 78 kilometers. So now earlier, when we get back to that question of how can I reach the point of GeoSat in 12 hours, we can take advantage of all of the rules of thumb we've learned up to this point to know that the orbital period of an NMC is 24 hours, yes. To move halfway through the orbital period of an NMC is going to be 12 hours, right? That's just applying those early rules of thumb. So a radial burn produces an NMC, and that means that if we want to reach GeoSat in 12 hours, an NMC shape is the perfect shape to take. So now let's combine all of the rules of thumb together, and let's see how we can get to GeoSat with a single radial burn in exactly 12 hours. Okay, so first rule of thumb we're going to use is that RPO satellite is starting out 1 degree away, which is 736 kilometers. Next rule of thumb we're going to use is that a 2.84 meters per second radial burn produces a semi-major axis NMC of 78 kilometers. So now what we're going to do is use this rule of thumb to figure out what is the halfway point between us to GeoSat. Another way you can think of the radial rule of thumb is that a 2.84 meters per second burn produces a 156 kilometer wide NMC. Okay, so let's just do some basic math. There's 736 kilometers in a single degree. One 2.84 meters per second burn produces a 156 wide NMC. So we want to find out how many 156 wide NMCs can we fit into 736 kilometers. Apparently it's 4.7. Now to produce an individual one of those NMCs, we just need to multiply by 2.84. So now we take this number, multiply by 2.84, and we get 13.498. So what we're going to do with our RPO radial satellite now is do a positive 13.398 meters per second burn. We're going to run it, and if we're geniuses, which we are, we will now demonstrate that we are at GeoSat in 12 hours. And here we go. We can already see that we're geniuses. Well done. But now let's just move 12 hours, and there we are, right at GeoSat. The radial rule of thumb. Now, like I said, I've already produced a lot of videos for how to combine these two effects. But once you start to think about it in this point of apparent motion, there's a lot of ways you can say, what if I want to move my point of apparent motion 78 kilometers over and 78 kilometers up? I'm going to have to combine a radial burn and an in-track burn. Or what if I'm 4 degrees away from GeoSat and I want to close that distance in 12 hours? How much would that take? Well, you just take this number that we've done for 1 degree and just multiply by 4 and understand that it's going to be 53 meters per second positive radial to move to GeoSat in 12 hours. Okay, guys, I think I'll leave it there for today. Just some basic rules of thumb that can help you start to understand how to move in the geosynchronous orbit. And I'll say that there are more out there. There's essentially an unlimited number of approximations and rules that you can produce that allow you to make more efficient decisions, more instinctual decisions, faster problem solving that allows you to solve more complex problems like, no, seriously, how do I get to this point right here, right? We haven't talked much about the cross-track rules of thumb, but I just want to leave you with some basic rules that can get you started in sort of this two-dimensional space, understanding the length of that space, the time scale, how to move in 24-hour motion, how to move in 12-hour motion, how to use in-track burns, how to use radial burns. How does your semi-major axis dictate your east and west drift around the Earth? Just some basic rules to get you guys started, and happy flying.